This is section 5.1 on normal and standard normal distributions. These are different type of probability distributions, and they are actually a continuous probability distribution. The ones that we've looked at before are discrete, and these deal with continuous data, so time, weight, anything that involves decimals and not just whole numbers in the data set. So a normal curve is talking about the graph of a normal distribution. And we've looked at normal curves before. It looks like a bell-shaped curve, which is actually the second property here on our list. So it's a bell-shaped, symmetric about the mean. So the mean is in the middle. The first property, that mean, median, and mode are all equal. The total area under the curve equals 1. So that comes from probability. If we have an 100% probability of something happening, that means the total probability we have is 1. So that's where that comes from. And the curve approaches the x-axis the further away it gets from the mean. So this is talking about the shape. And we draw, so here's our x-axis, a horizontal axis. Here is our normal curve right along that. So it gets closer the further away it gets from the mean, so the further away it gets from the middle. And between one standard deviation from the mean on either side of the graph, curves down, and outside curves up. So what that means, so if this is about one standard deviation, so this is +1, this is -1, what that means is we have these inflection points. So a point here and a point here. So these points, which are called inflection points, are important because they tell us where our standard deviation is. So, but from the mean to each of these, we are curving down. So it's talking about this part. And then after each of them, it starts to curve up and out towards the x-axis. So that being said, we can do a couple examples. So here we have this example that shows our mean and where our standard deviation is. So the mean is always in the middle, and we are going to use mu to represent the mean. So mu, it kind of looks like an M and a U combined, and this dotted line is pointing to about 3.5 as our mean. Our standard deviation from there would be how far away are our inflection points. So if we draw a little dotted line down, we have 5 and 2 are what match up with the inflection points. So to get our standard deviation, we can do 5 minus 3.5. We want to figure out what is that distance. So the distance would be 1.5 as our standard deviation. We could do it the same way going the opposite. So 3.5 minus 2 also gives us 1.5. So standard deviation is the distance from the mean to either of the inflection points, and it'll be the same on both sides. For this example, we have the same mean, so the mean is still 3.5, but our standard deviation is different. So now our inflection points line up with 2.5 and 4.5. So that means I have a standard deviation of 1. You'll notice my graph is skinnier. So the larger my standard deviation, the wider the graph, the smaller it is, the skinnier the graph. And our last one, so here our mean is 1.5, and our inflection points line up with 2.5 and 0.5. So we have a standard deviation of 1, and you can tell the curve is very similar in shape. It's the same width. But this one is moved more over to the right, whereas this one is moved to the left. So the bigger your mean, the farther it is to the right. The smaller the mean, the further it is to the left. So for this example, understanding the mean and standard deviations, determining which curve has a greater mean would mean which curve is the furthest to the right. And then which curve has the greater standard deviation, that would mean which curve is the widest. So farthest to the right, and then for standard deviation, whichever one is the widest. So those are the two things you would look for. So for this first example, B would be the one with the largest mean. As we can see, the mean here is 60, and these two, A and C, both have a mean of about 45. So B has the largest mean because it's the furthest to the right. And 2, in this case, a greatest standard deviation, that would be C because C is the widest. A and B look pretty similar in skinniness. Looking at this example, which normal curve has the greater mean? So that would be A. A's mean is 15, whereas B's looks like it's about 12. So A is further to the right. Who has the greater standard deviation? That would definitely be B. You can see B is a lot wider than A. So this example says the height and feet of a full-grown oak tree are normally distributed, the heights. So like I said, continuous data, heights is a form of continuous data. The normal curve shown below represents this distribution. What is the mean height of a fully grown white oak tree? Estimate the standard deviation as well. So based off of this graph, the mean is always in the middle. We take a line and put it right down the middle. Our mean height would be 90. Now, the reason it says estimate the standard deviation is because we kind of have to pick where the points of inflection are. So where does it start to curve? So I'm going to say like right about here and here. Keep in mind it's going to be the same on both sides. So let's see. So if this is 95, 1, 2, out to 93, and about 87. So we're going to say that our standard deviation is about 3. If you picked it and yours is about 3.5 or about 4, because it is an estimation, sometimes the values are a little bit off.